is 7:33 a.m. Central Time on the 4th of November. It is therefore the day after the election here in the United States. We don't really know the results yet, so we'll have to see. So yeah, let's get started with some organic chemistry because that's exactly what we need to do right now. Organic chemistry train never stops. Today we'll be doing some hydroboration reactions. Hopefully I remember the mechanism. Let's just review it for a second. Not likely that I remember, but we'll see. So if we have an alkene like this with a hydrogen on it, hydroboration, we're going to be adding THF as well as BH3, this complex molecule here, and then we're going to end up getting anti-Markovnikov. So that means we're going to add the boron to the least substituted carbon, and the hydrogen to the most substituted one. So it should be like this. And then once we have that molecule, we're gonna react it with peroxide, I think. Yeah, peroxide and hydroxides to remove the boron and replace it with the hydroxyl group. And so then we get an anti-Markovnikov alcohol. So the first problem, let's see, show how to turn 1-methylcyclopentanol to 2-methylcyclopentanol. Okay. So our reaction is going to be cyclopentanol, huh? So 5 sides, 1-methylcyclopentanol. And then we're going to have to turn that into 2-methylcyclopentanol. So how are we going to do this? We need to work backwards. So what can we do to make this into, to make this? Well, we're going to need to put, okay, so we're going to need to have some sort of alkene like this. So we need to have this alkene. We can turn it into this thing through our hydroboration. And we can tell that it's going to be the hydroboration because if we use the mercury method, or we used acid catalyzed hydration, then the OH would instead go down to here and we'd get the same molecule we started with. So how do we get from this thing to here then? Let's just call this hydroboration. So how do we get to here? Well, it looks like we're gonna have to do a dehydration reaction to get rid of the OH group. So how would we do this? We'd first start with the pentanol thing, the methylcyclopentanol, and we treat it with strong acid to get an alkene like this. Yeah, to get this alkene, which is the same thing as this alkene. These are the same molecule, as far as I know. Yeah, you can just rotate it and it'll be the same molecule. And then we can use BH3 THF to turn it into this with the BH3 right there, and then we can douse it in peroxides, H2O2, and hydroxide. So I guess that'll be like NaOH or something. And then that'll turn our molecule into this thing. Which is what we want. And I think that's what we need here. Yep, nice. So there's that problem. What next? Next problem. We're going to need to do... Okay, so predict the major products. Okay. Oh, spelled predict wrong, but whatever. I don't even know how to spell to do chemistry. Oh, that's a lie, you do. Propane plus... I'm just going to say BH3. Technically it's BH3THF, but I'm just going to write BH3. That product plus peroxides and... Okay, well, I think we know where this is going. 2-methyl-pentuene plus BH3THF. D is the same thing, but with peroxides and hydroxides. And then 1-methyl-cyclohexene plus BH3THF. And, okay, yeah. So let's get started here. First one is propane and BH3THF. So if we have propene, what am I doing? Not cyclopropene. Propene, so, nope. Propene plus BH3THF. So let's think, which one is the least substituted carbon here? It'll have to be this one, and then this one is the most substituted one. So our product is going to be this. And just to be clear, I'll write out the hydrogens as well. I'll just say this is CH3 so I don't have to write out the hydrogens. So hydrogens like this, so this will be our product from that. And then once we treat it with peroxides and hydroxides, that makes it look like methanol. Then we're gonna get this thing. So yeah, that is our alcohol. We get ethanol, or no, that's 1, 2, 3. That is propanol. Okay, so next we have 2-methyl-pentuene. So 1, 2, 3, 1, 2, 3, 4, 5. Pentuene. 2-methyl-pentuene added with the BH3THF. So which one of these is the least substituted carbon on the double bond? So this is going to be the least substituted carbon. This is going to be the most substituted carbon. So that means our product's going to be something like this. Or, let me see. Yeah, something like this. Where one of these is a hydrogen. Okay, and then once we add H2O2, as well as hydroxide. I'm just going to start writing NaOH instead, probably, because this looks like methanol, and we're not adding methanol. That's completely different. So now we should get our alcohol. So what is this even? 1, 2, 3, 4, 5. Pent3-ol. Pentan3-ol, and then it has it's 2-methyl pentan3-ol, isn't it? Yeah, that looks right. Okay. And so now we have 1-methyl-cyclohexene. Methylcyclohexene. So 1-methyl-cyclohexene plus BH3THF. And so which one is the least substituted carbon? This is the least substituted carbon. This is the most substituted carbon. So that means we're gonna get BH3 like this. And then when we treat it with these things, we're gonna get our nice cyclohexanol. Yay. So let's see if we're right. Check the answer key. 10. Looks like yes, that is what we get for all of these. Oh, that's right. Stereochemistry. You can't ignore stereochemistry with these, apparently. It's a sin addition. So for this will be M like that with the H and that. Or we could have the enantiomer. I knew I was going to forget something. We can have the enantiomer like this. So yeah, that means that we're going to get the enantiomer as well. Okay. So there's that problem. There's that problem done. Next problem. How would we accomplish the following synthetic conversions? Classic problems. Hopefully I'm getting better at these, but you know. Let's see. But1ene to butan1-ol. But1ene to butan2-ol. Okay, so this one's a lot more complicated. 2-bromo 2,4-dimethyl-pentane to 2,4-dimethyl-pentan-3-ol. Okay. Interesting problems. Let's get started with but1ene to butan2-ol. So these look like to be, these two look like to be like Markovnikov and anti-Markovnikov type of things, but I'm not sure. Let's check it out. So we have here, we have to turn it to butan1-ol, so like this, or butan2-ol, which is like this. So it looks like, well, here, let's first determine our most and least substituted carbon. This is least substituted, this is most substituted. So it looks like this one over here is going to be the anti-Markovnikov product, whereas this one is going to be the Markovnikov one. So that must mean that for the first one here, we're going to have to do the hydroboration thing that we've been doing. So we get this, and then we treat it with peroxides and hydroxides, and we're gonna get this thing. Okay, so now we have this thing. How are we gonna do this? We can either do it with acid catalyzed hydration, but if we do that, will there be any hydride shifts? I don't think there will be. So we can do it like this, H2SO4 with water. Acid hydrolyzed. Acid catalyzed hydration. That's gonna give us a carbocation like this. And then what's next? I forget. Oh, I think what happens next is that the water gets added, this, and then it gets deprotonated. Okay. Now, if we look at this, yeah, I think this is the best carbocation that could form. I don't think any other carbocation is forming. Or we could do the mercury method with mercury acetate. And what else was the solvent there? I don't really remember. I think it's that in water. And then we end up getting this thing, the acetate, mercury acetate, like this. And then what we get? I'm trying to remember my mechanisms here. This is kind of a struggle. Like this, maybe? Okay, yeah, like this. And then we treat it with something to do with boron. Oh, right. Sodium boron thing. And we get that. Cool, so that's 3 different ways we can get that. So now let's think about 2-bromo 2,4-dimethylpentane. So pentane, 1, 2, 3, 4, 5, 2,4-dimethylpentane. So 2-bromo 2,4-dimethylpentane, and we have to turn that into 2,4-dimethylpentanol. So 2,4-dimethylpentan-3-ol. Okay, so how do we get to this molecule? Well, we're going to need an alkene. So let me just say that this is an alkene. And so is this a Markovnikov or anti-Markovnikov substitution here? This is less substituted than this one, so this must be anti-Markovnikov. So it looks like for our what we're going to do here is first second we're going to have our hydrobromation. And so how do we get from here to here? Well, I think we can just do a dehydrohalogenation E2 style. So can we do an E2 style? Yes, because this is a triply substituted carbon. It's not going to do SN2. Yeah, so that means that we should start off with, what's a good E2 solvent? How about something like, oh, well, we're going to use it later anyway, so sodium hydroxide. How about we use sodium hydroxide in water? And that'll give us our alkene here, like that. And then if we hydrobromate it, we're going to, hydrobromate it, we're going to get this thing. And then peroxides, as well as the sodium hydroxide from before. Oh, I guess it doesn't have to be from, whatever. I guess we could we just make it a solvent of sodium hydroxide and peroxides? Wait, does that work? Does the sodium dissociate in that? I'm not sure. I'm just gonna play it safe and say remove it to a different beaker. And so now we get our, oh, I drew that wrong. Now we get our alcohol that we wanted. There we are. So let's see if these were correct. I'll check this one first. Yeah, looks like I was correct in my mechanism. I guess I should have added a lot of heat to make sure this was an E2 reaction. But I don't think that was really necessary necessary, given the sterics of this carbon right here. Now, how about our other reactions that we wrote? Yeah, looks like I'm correct here. Stereochemistry. I keep messing up with the stereochemistry here. Apparently this is going to be a racemic mixture. down here. Well, makes sense how this is a racemic mixture because you can add the water to either side. It's an SN1 reaction. Now, the question is why, or SN1, is that really a good word for it? SN1-like reaction. Now, why is this one racemic? Why does this add racemically? Well, yeah, because I guess the mercury can add from either side. It can add from it can add into the page or it can add out of the page like that. So it really could be, it's racemic. I really need to think about that. I'll try to think about that on the next couple of problems I do here. Let's see. Let's see. Okay, norborine. Okay. Let's see. I'll just draw it. How about we do this? D. And it is subject to this thing. We have to give the structures of the products. Okay, so now the question is, which side does the boron attach to? Is it on from below or from above? So I guess we have to pick a side here. I know there's a rule for this, I just don't remember if it's the bottom face or the top face. Which looks more likely? Well, it kind of looks like to me that the bottom is more bulky than the top. So I'm going to hazard a guess and say that it will end up like this, with the hydrogen like this and the BH3 like this. Yeah, both are equally substituted. And then we're going to get our alcohol that looks like this. I wonder if that's correct. Wait a second, have I been doing this incorrectly? Yes, I have been doing it incorrectly. It looks like we're not actually substituting BH3 here, we're substituting BH2. That's pretty important, and I should not mess it up anymore. Okay. Why is this? Why do we add from the top? Apparently we add from the exo side, but what does that mean? Norborine. Add from the exo side. I guess that does mean we add from the top, right, then? Let's look up what exo means exactly. I'm not sure what that actually means. Okay, so it is exactly what I think it means. It's top versus bottom. Why do they call it that? Anyway, whatever. A lot of stupid stuff in organic chemistry I don't understand. Well, I guess that makes me the stupid one, not the chemistry. Let's see. Problem next. Okay. Okay, so in the hydroboration of 1-methyl cyclopentene, the reagents, can't spell reagents, are achiral and the products are chiral. The product is a racemic mixture of trans 2-methyl cyclopentanol, but only one enantiomer is shown. Show how the other enantiomer is formed. Okay, so hydroboration of 1-methyl cyclopentene. We did this a little bit ago. Cyclopentene, yeah. I think that was the first problem we did, maybe. The reagents are achiral, and the product is a racemic mixture of trans-methyl cyclopentanol. So, let's see. Bam. Bam. Bam, 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 bam. I'll just write it like this to do it all in one step. I don't want to write out both. So one enantiomer is shown. Show how the other enantiomer is formed. Well, it's pretty simple, right? You just either add from this side or this side. I don't really see what the problem here is. You either add from like into the page or out of the page. It's like I don't know how to, maybe like, if we say that I'll draw it. Like, ooh, I can't draw. Okay, if we like do this, you can either attack from the top or from the bottom. So yeah, that's how the enantiomers are formed. That should be it. Yeah, and looks like I'm correct there. Okay, next problem. Okay, now we have to predict major products. Include stereochemistry. Okay, so we have 1-methyl cycloheptene plus BH3THF and H2O2 and OH minus. Okay, trans 4,4 dimethyl pent 2-ene full hydroboration. I'll just call it full hydroboration, and then some kind of strange norborine type of molecule. It's methyl norborine, I think what you call it. I don't know how to name those. It's this thing. And then you do a full hydroboration. Okay, so first problem, 1-methyl cycloheptene. Have I gotten better at drawing cycloheptene? Let's hope so. Oh god, does not look like it. Okay, Jesus, how do I draw this thing? 1, 2, 3, 4. Guess God. How about that? Yeah, there we go. 1-methyl cycloheptene. Okay. And then we have to go the full hydroboration. So if we do the BH3THF here, we can attack from either into the page or out of the page. So it could either be like this, with the methyl pointing in like that, or we could have it like, oh, whoa, whoa, what am I doing? That is the wrong reaction. It could either be like this, where we have the methyl like that and the BH2 like this, and they have to be trans to each other because we're adding we're adding syn. The hydrogen that's added is syn. Or we could have bam, 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 bam. Oh, my molecules are getting smaller and smaller. Methyl like that, and we could have the BH2 H, and then it goes the full hydroboration, and then we end up getting. I don't want to draw it again. You get the point. We can just replace this with OH. There we go. Okay. And then trans 4,4-dimethyl pentuene. 1, 2, 3, 4, 5. 4,4-dimethyl pentuene. Okay, well, pentuene, and then 4,4. What? Wait, how's this trans? Oh, yeah, I don't know. Dimethyl pentuene. What, like that? 1, 2, 3, 4 dimethyl pentuene. Okay, yeah. Yeah, okay, yes, this is trans. And then stereochemistry. I'll just do it all in one step again. Do it one step. Okay, so what's the least substituted carbon here? Oh, they're both least substituted. Oh, that might be a problem. Okay. So I guess that means we can have what? We can have, well, first let's draw this. Okay, so we could have hydroxide over here, like that. And then what? These are both H's. Okay. So we could have that. Or it could be this. Wait, but are these the same molecule? Let's think about this for a second. Are these the same molecule? No, I think they're enantiomers. Yeah, okay, yeah, they're enantiomers. These are enantiomers of each other. Or we could get the diastereomer. We could get, what, like, oh god, this is, you can get it like this. Bam, bam, bam. These are the hydrogens. And then we could get where the oxygen is back, and the hydrogen is forward. H. Oh, that's not an H. Okay. Yeah, I guess that's what we're getting. It's kind of want to check, but we'll do that afterwards. Let's do this other problem now. Full hydroboration of this norborane thing. Okay, so I think there's only going to be 2 results we get here. We're gonna have to add from the top, I think. Yeah, I think we're adding from the top, and we add on to the least substituted. So, oh Jesus, why did I say it like that? So we could have this, or we could have this. Wait, no, we couldn't. No, we couldn't. Oh, I guess this is the only product we can have then, because it has to be anti-Markovnikov and also has to be exo. So there's no way for it. Yeah, so this is the only result we have. Let's check. Nice. I'm correct. Now. So I'm correct on that one. Apparently I'm not right on the other ones. Well, first... Okay, well, this one's correct. What is wrong with this one? Let's see. Transform to in. Oh, I guess I had a... Well, I thought these would all be the same, whatchamacallit, prevalence. But... I guess, yeah, I guess this one's minor, and this one is major. And the reason this one's minor is because there's steric hindrance of the BH3 attacking from all these methyls here, so I guess we have to think about sterics as well. I guess that makes sense because BH3 is so bulky, it's going to definitely be affected by sterics. Okay, that's something to take into account. I thought I got the stereochemistry stuff right, though. Feel good about that. Okay, let's see. And then let's do 2 more problems. Or more, maybe more than that. I don't know. Yeah, okay. So, predict the major products. Nope, we already did that. Okay, so when Z3-methyl-hex-3-ene undergoes hydroboration oxidation, 2 isomeric products are formed. Give their structures... Okay, yeah, so... Whoa, I didn't even type it. What happened? I didn't type. Okay. What was it? Z3... What the... Jeez, okay. Z3 methyl hex 3-ene hydroboration oxidation 2 isomeric products. Okay, so let's figure out. Oh, we also have to label their S configuration, R configuration, all that kind of stuff. So methyl hex 3-ene. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. Z means that it's Zamzide. So I guess it's like this. That's the molecule we have. Okay. And then 3-methyl X3. Okay, that. Do I remember my Z? I think that's Z. That's gotta be Z. Okay. We get 2 isomeric products with BH3, THF, H2O2, hydroxide. So, what are the 2 isomeric products we get? Well, it's not going to be diastereomers because you're going to only add the OH on one side. So let's do this. So that goes to the back. This one also goes to the back, like this. I messed up big time drawing this, didn't I? How do I draw this? I guess let's draw the hydrogen right there. So like, OH back there as well, and then so like this. Okay, and then we can also get where the hydrogen is the one in the back, like this, and the methyl is the one in the back. With the hydrogen in the front, and the OH in the front as well. So what do you call these? Yeah, good question. I think they're enantiomers. Yeah, they're enantiomers. Or are they the same molecule? Are they the same molecule? Let me think if there's any way I could switch around in my head to make it the same molecule. Yeah, it doesn't look like it. Yeah, no, don't look like it. Okay, so then we have to repeat it for E. Okay, so then we have to repeat the E configuration. Okay. I wonder if this is going to be any different. E configuration will give us the following. God. Well, give us this. We have to figure out if it goes like... I guess this is the much easier way of writing things. Is to do it like this. Okay, and we also get this thing. Yay. Right? I think. So are these enantiomers? Aren't they always enantiomers? I feel like I'm missing something here. Yeah, I feel like it's also enantiomeric. Yeah, must be, right? Well, I'll find out, I guess. Oh, I forgot to do the stereochemistry thing. Okay, so this carbon, we have a hydrogen right here. We have what? So it's gonna be 1 that direction, 2 this direction, 3 this direction. So what? That's counterclockwise. Hydrogen's pointing the other way. So that's S. Then this one over here, it's gonna be 1. Man, 2, I guess, and then 3. So then, what we get? 1, 2, 3. Is this also S? I think this is also S. I kind of drew this like an idiot, but yeah, it should be S. And so then this one should be R. This one should be also R. I'll just verify with this part over here. This should be 1, 2, 3, clockwise, pointing into the page. Yeah, must be R. Okay. So then this over here, this will be 1 that direction, 2 that direction, 3 this direction. This will be S. This will be so 1, 2, 3. this also S? No, that can't be right. That can't be right. Is that right? Is that also S? Did I even draw the strat? No, I didn't even. Oh dear lord. I already messed up. That revealed how I messed up. Okay, let's redraw this. Okay, let's redraw this. Yeah, because no way they both have the same stereochemistry. That doesn't make any sense. So it has to be the hydrogens have to be on the same side. Sin addition. HOH. Like this. Like this. Jesus. Discord, please. God. Okay. Sorry about that. So then this. God. Man, these problems are always the worst. I hate this. Like. Stereochemistry. I don't know how to decide how it goes. Whatever. I need to do more stereochemistry problems, clearly. So then this over here is 1, 2, 3, pointing out of the page. So counterclockwise pointing out of the page must be R configuration. And then I'm guessing this will be S configuration now that I did. Oh, by the way, I forgot to write in my hydrogen. Awesome. Okay, so this will be 1, 2, 3, counterclockwise. Yeah, so that must be our S and then the enantiomer. Oh god, what a pain. What a pain. Right? What a pain. Okay, so then this one should be S, R. Right? 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 Yeah. Wait. Oh god, did I do the stereochemistry wrong? I'm just so done with all. No, wait, no, I didn't. Oh, nice. I did get it right. Oh my god. This is the worst. I hate stereochemistry stuff. Well, there's that problem. That was really fun. Let's do one more. Never stop. Okay. Show how it would accomplish the following transformations. Okay, I'm not gonna write out the problem because we're kind of running out of time. I want to keep this to about an hour, but I guess there's really no rush. So, how would we do the following transformations? OH. Okay. So this one, how do we do this one? Well, this looks to be a Markovnikov substitution, so I'm gonna do this. Yeah, is it Markovnikov? Yes, it is Markovnikov. This is the most substituted carbon. So I'm gonna treat it with acid H2SO. Is that safe? Is that a good thing? I feel like I should just always do this thing. Yeah, what is the solvent here exactly? It's just water, right? Yeah, it's gotta be. Okay. And then we're gonna get a nice this thing. Then you add this thing. Do I need to I wonder if I need to include the hydroxides, because you technically need it. Whatever. So what we get? Our product, yay. Okay, let me check if that's correct. Yep. Of course, it's expected of a genius like me. Bam, 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 bam. Same molecule. Oh, I can't draw. Same molecule, but this time the oxygen, the hydroxyl's on over here. Okay, so this is pretty clear, right? Like, we gotta do the hydroboration, we do the H3 THF, we end up getting our BH2, and you add your peroxide, hydroxide, and we get our that thing. Yep. Okay. So 1-methyl cycloheptanol. 1-methyl cycloheptanol. I turn that to 2-methyl cycloheptanol. Didn't we already do this? I think we already did this problem. Two methyl cycloheptanol. Yeah, I definitely feel like we already did this, but what you gotta do is you gotta. Oh god, I can't draw. You gotta do this thing, so you get the alkene. This. And then it's a anti-Markovnikov, so you do the hydroboration, oxidation. And then we get this thing. Yay! Did we get it right? Jesus Christ. I forgot the stereochemistry again. Yeah, so you can either get this thing, or you can get this thing. Of course I forget the stereochemistry. Same thing here, you can also get the enantiomer, right? Of course, I always forget. Okay, so one more problem. We have to show that the reaction of HBr plus 1,2-dimethyl cyclopentene is not stereospecific. And we also to show that hydroboration oxidation of 1,2-dimethyl cyclopentene is stereospecific. Okay. Let's do that. Oh, no, my background. Okay, cool. Nice. Okay. First we gotta do our dimethylcyclopentene. Oh, where is my pen? There it is. Dimethylcyclopentene. One, two. Bam. It's not stereospecific. Well, this is not stereospecific because both of the carbons are equally substituted, and you can add from either direction. So yeah, that's why that's not stereospecific. Yeah, I feel like that's pretty simple. Unless, like, I mean, what's the reaction with HBr even? It's, yeah, you can add from any direction. But let's, for fun, let's figure out what the product of this would be. It would be an anti-addition, wouldn't it? This would be a Markovnikov anti-addition. So it'd be like BR like this. So it would be like this, right? It's an anti-addition. Now, why is it an anti-addition? Good question. I don't know. Huh. Bromination of alkenes. I forgot exactly how this mechanism is. Is it anti? Yeah, it's gotta be anti, right? Hydrohalogenation, sorry, of alkenes. Does it even have to be anti? Whatever, I'll check. Oh, it forms a that's right, it forms a carbocation, so it doesn't have to be. Okay, well. I'm actually gonna end the stream here. Have a nice day, everyone.